In this video, I want to give you a few tips on solving these multi-stage chillers that are often used for liquefying natural gas. You'll see that our setup here looks pretty straightforward. We have our natural gas and our propane that we're exchanging heat with. We're using 4 stages in this case of what I'll call a core and kettle style, meaning that our natural gas is passing through these exchanger cores, and then our propane is sitting in these different kettles, beginning at a high pressure kettle and then working its way down to our lowest pressure kettle. And so what happens on the propane side is our liquid propane comes into this first kettle. Some of the propane is vaporized, and some of the liquid propane then moves down or passes to the next kettle on down to the lowest pressure kettle at the end. And by the end, in that last kettle, we're going to vaporize all of our propane. That propane will then all be returned to a propane compressor, and our cycle will start over again. Now on the natural gas side, we know what's going on. We're just cooling down from our beginning temperature to our desired final temperature as a liquid. And so our goal in these systems usually is to determine how much propane is required to do this chilling. And so I'll give you a few tips as we go through this, but to start, your first inclination might be to create a solver on the propane flow rate, and so that we have 100% vapor in this final kettle. So let me open up this propane stream, and you'll see that I've started that solver already. If I open it up, our equation here is our MFV, or our mole fraction vapor, which we want to have be 100%. And so that's our goal. With this solver, we need to put in a calculated value. And so this is going to be our initial estimate, and then ProMax will adjust this to the final answer. And to begin with, I'm just going to throw out a number, say 100,000 pounds, and click execute. When I click execute, if we go back to the page, we'll see that that number didn't change and that some of these blocks stayed blue. If we look at our warnings at the bottom, we'll see that those blocks have actually failed, and so that's failed the solver and kept the solver from finding a final solution. And the reason for that is we started with such a low guess that all of the propane vaporized in this first kettle, and so we actually have 0 flow going to the next 3 kettles. And so it's important to have a good initial estimate and to have a high initial estimate in order to get this thing started. Now, in order to come up with that estimate, we could just keep manually guessing until we find a number that works, but it would be nice to have a method for coming up with a good guess. And so here on the left, you'll see I've set up this test exchanger. And what I'm doing here is I'm first recognizing that I do know the total amount of duty that I require for my propane chiller. Right? So the total duty would be the summation of the 4 duties from these 4 core exchangers. And so what I've done over here in my test exchanger is, first off, in this energy stream, if I open that up, you'll see that I've put a specifier here. And what that specifier is doing is it's just summing up those 4 energy streams, and so now this is my total energy, or the total duty required. So with that total duty, what I'm going to do is I'm just going to take a propane stream and start it at my initial conditions, which were 95 degrees and 217 pounds. And then I'm going to set the outlet as what I'd like my final conditions of my propane to be, which is 100% vapor at my low pressure kettle. So if I double click on this stream, for my pressure, I'll set this to my low pressure kettle pressure, 3 pounds and 100% vapor. Okay, and with that set, ProMax will now calculate how much propane would be required in this little test exchanger I've set up, which is going to be a decent estimate of what is needed overall in my actual setup. We'll see that the mass flow it calculates is around 900,000 pounds per hour. And so I'm going to come back into my propane stream. I'll right click here, and I'm going to start at 900,000 instead. 900,000 for my initial guess. Okay, and I'll go ahead and execute now. I'll let that run here for a second. You'll see that it does converge. It comes to a solution. I'm 100% vapor at this point. But you'll notice that we have an error here, and it's saying I've got a negative approach temperature in my final kettle. If I open up that kettle, we'll see what's happening here on our plots. The blue line represents our propane, and we reach a point where we get this drastic increase in temperature, and what that means is that our propane is superheated coming out of this kettle. And so the problem we've run into is we've tried to aim for 100% vapor, but 100% vapor can be at many different conditions. It can be right at the saturation point, right where it's just barely vaporized, or it can be anywhere in the superheated region. And so this isn't what we want to have occur. We want to just barely vaporize all the propane, meaning that that vaporized propane will be at its dew point when it comes out. And so we need to adjust our solver somehow to get us to be at the dew point and not just be at 100% vapor. If I go back into my propane solver, let's take a look at it. You'll notice here below my measured variables say that I am 100% vapor, but below that I have my current temperature, which has gone up drastically, and then the actual dew point temperature of that stream. Okay, and these are variables I just grabbed out of stream number 22. But I want these to be equal while also staying at 100% vapor. And so we can write some more complex math, use some scripting here in our equation in order to keep us at 100% vapor and also at our dew point temperature. So I'm going to write an if statement based on whether or not I am less than 100% vapor. If I'm less than 100% vapor, then I want my solver to get me to 100% vapor, like it was before. And else, meaning if we are at 100% vapor, I then want the solver to focus on getting my actual temperature to equal the dew point temperature. Okay, and so this is a little bit more complex solver, but this if statement is going to get us down to our dew point. Now, one other thing you can do with scripting is you can also add comments. And so if you ever just want to add some comments here above, maybe to just explain to ourselves what we're doing in case we ever need to refer back to this later. If I do 2 slashes like so, anything I write in this sentence afterwards is just going to be words. It's just going to be a comment here. And so I'm just going to comment what this is doing for me so I can remember in the future that I set this up to make sure I'm at 100% vapor and at my dew point. Okay, so that's just a little tip as far as scripting goes. So with that in place, I'm going to reset my initial guess, and I'm going to go ahead and execute. We'll see that it's now aiming for both these two things, making sure we're at the dew point and that we have vaporized, we're 100% vapor. And it oscillates quite a bit in its current setup. This error, you'll notice, is oscillating from positive to negative, pretty big jumps. And this will eventually solve, so let's give it just a second to get to that point, and then I'll show you a tip to maybe make this converge a little quicker. Alright, there we go. And so since this is a discontinuous function, as an if-else, kind of a piecewise function, we can use a different algorithm to kind of make this solver more robust in this case. So if I come down to my algorithms, there's the default, and then there's one algorithm here called the golden section, and this algorithm is meant specifically to be more robust for these discontinuous functions. So with that algorithm set, we also need to either set bounds or a step size that we would like it to take. Since our initial guess or initial estimate was 900,000, I'm just going to do 10% of that and say 90,000 as a step size. I'm going to reset this to 900,000, and we'll just execute this again to see if it runs a little more smoothly. We'll see that that's running. Our error is still changing, getting towards our solution, but it's not quite as jumpy, a little more robust, and did solve a little bit faster for us. So that's just an additional tip for you to keep in mind. So that's the end of this demonstration, and I hope that video is really helpful for you.